Hey there, in this video I want to talk about another popular family of minimizers called gradient descent. So the idea with gradient descent is you have a function, and it might be a multivariate function. So the bold x here is a vector, and it could have x, y, z components. It can have any number of components. And what we're going to do is to find a new value for this vector x, we're going to take the old value and we're going to subtract multiples of the gradient. This should kind of look familiar. This looks a lot like the Newton-Raphson method. The only difference is we have this extra constant gamma in here. And gamma is something we have to set. It's kind of like an art to set gamma so that if you pick gamma too tiny, your steps will be very small and it'll take a really long time to converge. And if you make gamma too big, your steps are too big and you keep jumping over the solution and your answer never converges. So you need sort of a just right gamma, and sort of the kind of parameter you kind of have to play around with. But other than that, it looks a lot like Newton-Raphson, where we're effectively just going downhill. We're taking x and we're taking steps downhill, going opposite the gradient. Remember that the gradient here is itself a vector quantity, and each component is based on taking a partial derivative. So let's just make this more concrete with an example. The function we're going to do be something nice and simple, nice and smooth. We'll do sine x times sine y. So we're going to start by defining that function of x and y, and we are going to return, well, just like I wrote, sine x times sine y. Oops, that's not how you spell sine. But we also need the components of the gradient here, so in this case we can calculate what those are analytically. In other cases you could do like a numerical version of this. So df dx, really partial f partial x, as a function of x and y, is going to be equal to cosine x times sine y, because derivative of sine is cosine. And likewise, we can calculate the partial with respect to y. So that would be sine x times cosine y. And then we could also make a function that represents the gradient. Let's call it grad f. And the gradient of f, we're going to write this one a little bit differently. Thinking ahead here, this is like a vector equation, which tells me that when we put this into computer code, we want these things, these x's here, to be arrays. So I want to write this as a function that takes an array. So xy will be an array that contains both x and y. Internally, I want to break those apart into their xy values. So we'll do tuple unpacking here. And when we're done, we want to return another array. And that array has two components that are the x and y component of the derivative. So df dx of x and y, and df dy of x and y. Okay, so this is just defining the functions we're going to end up using. Now let's make a visualization of what sine x times sine y looks like, and we'll visually inspect that to spot where the minima are. So this is your typical plotting of a 2D function here. We're going to create a mesh grid, and to do that we're going to need x values and y values. We'll make it a square. And we'll linspace this thing from, let's go negative pi to pi. And let's do 101. A nice odd number of grid points gives us a grid point right in the very center. And then we can get x and y using mesh grid, numpy.meshgrid. We give that x range and y range. Now, since we're doing a gradient here, gradient descent method, it would be nice to plot the gradient. And if you remember, we can do that using a quiver plot. When we do that, we don't want to use a high resolution grid. So like this 101 by 101 is not a great choice. We'd like something that's like maybe 1/10 that resolution. So let's calculate another set of values, x2 and y2, that are lower res versions. So for x2, we'll take x, and we'll start at 5 and slice every 10. We'll do that in both of its 2 dimensions. And then the same thing for y. And so what this does is just makes x2 and y2 lower resolution. Let's make sure that code runs. Oh, no. Yeah, I didn't spell it right. Here we go. Now we're going to make our graph here. Since we're making a fancy graph, let's just make it a little bit bigger than normal. And then we're going to imshow. We'll show the original function, f of x and y. Remember, your origin equals lower, so things aren't rotated on us. And just to help us spot what the actual limits are, we should put those in here. So negative pi to pi for x, and negative pi to pi for y. And our choice here for how we want to color it. I'm going to go with cool warm, so that gives us reds through blues with kind of a gray color in between them. And then we're going to do our quiver plot on top to show the gradient. So that's going to be our lower resolution x2 and y2. The components of that are df dx and df dy. Those are functions, and we're going to call them using the lower resolution x2 and y2. Last time we used quiver plots, I just put the slicing right in line here when I did the quiver, but this is just a different way of doing it. So I just, on its own line, define new arrays x2 and y2. Makes this a little bit shorter of a statement. Last thing we should add is to put the pivot in the middle. I mean, this is all just to make it look nice, but we've learned how to make it look nice, so we might as well reinforce that. Okay, and if everything goes well, this should make a graph for us. If it doesn't go well, what did I do wrong? Oh, this is supposed to be extent equals. And now what did I do wrong? Float object has no attribute np. Oh, it's not happy right here. That's supposed to be a comma. Okay, one more thing it's mad about. XY. Oh, because I typed in the wrong thing. But nice, it tells me what's wrong. Okay, so, oh man. Cosine is not defined. Oh, it's up here. Finally. All right, so we've got our gradient, and gradients point uphill. That's your quick sanity check here. So the red here, these are the bigger values. Gradients pointing uphill and out of the 2 minima. So we got a minima over here and over here. And of course, this is a periodic function, so there will be minima actually all over the place. But in the range that we've plotted, there's one over here and over here. So let's go and use a gradient descent. Let's put our starting point like almost at the center, but a little bit more towards this bottom right, and see that it effectively rolls downhill and finds the minimum for us. So I want to keep track of the values we calculated, because I'm going to draw them on top of our plot just to see what it looks like as it does a gradient descent. And we're going to make our array of values named x0, representing the point we're trying to find. This is an array, and I don't want to use the symbol x because I've already used that in a mesh grid, and I don't want to mess up calling those functions I wrote earlier, so I'm using a different variable name here just to protect me from that error. And as we just saw, I'm making a whole bunch of errors right now. So we're going to make the that array is going to be starting with our initial guess. And so I'm going to start at, if I want that corner, see, that would be an x coordinate of just a little bit more than 0 and a y coordinate that's just a little bit negative. So we'll make that 0.1 and negative 0.1. And then we're going to see how that rolls downhill. Like, yes, I mean, I can spot really clearly where the minima are. That's not the point. It's just to see how it works. So we start with a guess. And now we need to have some kind of step size that is represented by this constant gamma up here. Since I have no particular idea what the best value is, I'm just going to start with 1. And we'll see if that converges. If it does, great. If it doesn't, we'll make it... If it doesn't converge, we'll make it smaller. If it takes a lot of steps, we'll make it bigger. That's how we can figure out what the best version of gamma is. So I'll make that a variable so it's easy for me to change, and I'll set it equal to 1 here. And we'll fix it if we have to. Now we'll do our loop. It'll be, we'll do 100. We'll see if we can converge in 100. And as we go through, I want to store the values. So we'll begin by storing the first value, and then each iteration will store a new one. So we're going to update x0 by setting it equal to the old value minus gamma multiplied by the gradient. And we called the gradient grad underscore f. And it takes x0 as an argument. So remember, this is an array. And if we come back up to where we defined our functions, we wrote it so that it takes an array. Will be our x0. It'll get split apart into x and y, and it'll call the other code that we wrote up above. And now it's a matter of checking for convergence. So we have this multi-dimensional thing we're trying to check. We want to make sure that x and y, as they change, are both less than our tolerance. There's a few ways to do that. We could split the values out and check them individually with an AND statement. I'm going to exploit the fact that these things are a vector, and I'm basically checking if the difference between two vectors is very tiny. And that's the magnitude. So from we could do SciPy's linalg, or we can do NumPy's linalg. I don't have linalg imported from SciPy, so I'm going to just do NumPy's version because I have that imported right now. I feel lazy. So either of them has this linalg norm. And what we're going to do is we're going to take the vector x0 and subtract the last thing we stored in the value. So that would be the previous value of that vector. And if that magnitude is less than 1 times 10 to the negative 8, then we can say, okay, good enough, we've converged. And in that case, we should print a success message that includes our values. So it would be an x equals y equals kind of business after I+1 iterations. Now for x, that's going to be the first thing in my vector. And then for y, that would be the second thing. So elements 0 and 1. After we're done with that, we want to break out of here. And if we fail to find a solution, we'll print our usual message. First of all, let's see if this works. So I got, this looks like pi on 2, negative pi on 2, and it only took 8 iterations. And if we look at our graph, surely, yep, pi on 2, negative pi on 2 is right where our solution is. Let's plot the different values we got as we went. We can just duplicate our plotting code, and I just want to plot as points the different values on top. We'll put that down here in this cell. And before we show it, we want to do something like plot the x values and the y values. So let's see how to do that. Right now, values is a list that contains arrays. I would rather that values be a two-dimensional array. And so I can do that just by redefining it as the array version of itself. Now I can go in here and I could slice out, basically I'm thinking about a 2D array. So it's got 8 different points in there. So it's kind of like it has 8 rows and 2 columns. And the first column is the x and the second column is the y. So if I do colon comma 0, that'll be all the x values. Colon comma 1 would be all the y values. And our previous plot was red and blue, so let's do like yellow dots or yellow spots on it. Okay, let's see if this will make a graph for me. And down here, so this will be our starting value at 0.1, negative 0.1, and then we took these steps downhill. There should be a total of 8 of them. It looks like a bunch are right on top of each other as we're just sort of trying to get that last little bit of tolerance down to 10 to the minus 8. You can see it pretty quickly goes downhill. It's a pretty quick method based on Newton-Raphson.